Greetings, I'm Edward Carter, and this is a presentation on Compositional World Models Embodied Multi-Agent Cooperation. Below you can see the authors and their respective institutes, ranging from the University of Massachusetts, Amherst, INS, the Chattanooga University, Peking University, Johns Hopkins University, and the Honda Research Institute, USA. Apologize. A quick abstract overview. This paper focuses on embodied agents that must work together, even though each agent only sees their first-person view of the environment. Planning in this environment or this setting is very difficult because the world dynamics depend on what all agents do, not just the one agent. Combo introduces a compositional world model that breaks joint actions into individual components and combines them using diffusion models. It's paired with vision learning models, VLMs, for intention tracking, action proposal, and outcome evaluation. In this approach, each agent's action becomes a separate text-conditioned diffusion component. These components are then composed and generate future world states. With this, the system is allowed to imagine how the world would change several steps into the future, enabling cooperative long horizon planning. From the experiments conducted, Combo achieved higher success rates and better efficiency across TDW gain, TDW cook, and TD fetch queue compared to the strong baselines like MAPO or COELA or LLAVA. The core motivation is to build a method to build embodied agents that can work together on tasks requiring visual understanding. These tasks include assembling objects, cooking, or solving puzzles, without the complete information. In realistic settings, agents only have egocentric or first-person cameras, and no one sees the full environment. This partial observability makes coordinated planning very hard. To cooperate, agents must be able to learn how everyone acting together will change the shared world, especially over multiple steps. Most current world models simulate how a single agent affects the world. They are not designed to handle the combined interacting effects of multiple agents acting at the same time. The believed impact is that the model can accurately predict multi-agent dynamics and understand partial observations, can dramatically improve joint efficiency, and solve tasks more intelligently. The key problem continues to focus or to emphasize the difficulty of a single agent only having a partial view. As we can see, partial egocentric observations include each agent can only see its own point of view. No one has full access to the full map or the global scene. This makes understanding the true world state extremely difficult. In multi-agent scenarios, the world state isn't based on one action. It's the result of all agents acting simultaneously. Modeling can be very complex in this environment. Because agents only see small portions of the environment, they must reconstruct a best guess of the complete world state before planning. When you have multiple agents choosing for multiple actions, the number of possible future trajectories increase exponentially. A naive or standard world model cannot scale this. The limitations exist in the world models. Most current approaches assume a single agent interacting with the environment. They don't factor in multiple coordinated actions, interactions, or collisions. To cooperate effectively, agents must guess what others will do, especially in tasks like passing objects, cutting food, or assembling puzzles. The need for long horizon reasoning. These tasks are often require several sequential steps. Good cooperation is not just about the next action. It's about predicting the effects of many future actions. The limitations of the prior method. As you can see, it was the single agent world models, no handling of joint actions, the dependency of full observability, long horizon planning, no intent interface, failure in complex visual tasks. To break these down, most agents or models currently only look at one agent action at a time. It's too limiting when several agents are acting at the same time. The environment changes on a combination of multiple actions, not just a single one. So without the modeling joint dynamics, predictions become inaccurate very quickly. Models rely on having access to the full world state, but in real embodied scenarios, agents only see through their cameras, which introduces uncertainty and missing information. Collaboration often requires planning multiple steps ahead. Planning breaks down when the model can't accurately simulate several future frames. Cooperative tasks need agents to predict others' potential actions. Prior work rarely includes mechanisms for understanding teammates' intent. The paper's experiments show that the recurrent world model of an MAPPO failed completely in these multi-agent visual tasks, reinforcing the need for a new approach. For laymen, the MAPPO stands for Multi-Agent Proximal Policy Optimization. It's a version of PPO, reinforcement learning algorithm, that has been adopted to handle multiple agents. PPO itself is a stable, widely used reinforcement learning method, and MAPO applies it to scenarios where several agents must learn to act together. In combo tasks, like TDW game or TDW cook, the agents only receive egocentric RGBD data or images and must reason visually about many objects. This scenario introduces high-dimensional observations, very complex physics, partial observability, multi-step, long-horizon planning, and interactions between simultaneous actions. Combos goes to allow embodied agents to imagine the future, specifically how multiple agents acting together will change the environment. This imagined future is then used for cooperative planning. Core ideal is compositional world model. Rather than treating joint actions as one complex action, Combo breaks them down into per agent components. An example of this is Alice picks up a lettuce, Bob waits, Charlie passes the plate. Each is modeled separately, then combined using diffusion-based compositional generation. The world state reconstruction. Agents don't see the whole scene. Combo reconstructs a top-down world state using partial RGBD observation and diffusion-based in-painting model. Planning models, VLMs or visual language models, powered. Combo adds 3 vision language components. The action proposer, which we'll get into later in this presentation. The action proposer, which suggests the next possible steps. The intent tracker, which is meant to predict the other agents might do, what they might do. And the outcome evaluated, which looks at if the actions lead to the desired end state. The planning process. Combo performs online planning using a search tree. Expand multiple possible futures, the search tree expands multiple possible futures, simulate each using the world model, and evaluates outcomes and keeps the best trajectories. The result, this combination produces a highly accurate predictions of multi-agent dynamics and enables effective cooperation, outperforming reinforced learning and previous large language models or visual language model approaches. The purpose of the compositional world model. This model is the core engine behind Combo. It predicts how the world will look after multiple agents take their actions at the same time. Instead of trying to learn one huge model that understands all combinations of actions, Combo breaks the joint actions into per agent textual descriptions. Another example, keeping with the Alice, Bob, and Charlie, is Alice picks up the blue piece, Bob moves left, and Charlie waits. This makes the problem much simpler and more modular. Each agent's action is passed into the video diffusion model conditioned on the current world frame. The diffusion model predicts the visual effects of the specific agent's action. These predicted effects are combined using the compositional score function, allowing the system to generate a single, unified feature frame that reflects all agents' actions together. Because actions are factorized, the approach generalizes to any number of agents, even more than it was trained on. The paper shows it performs well with 4, 3, and 2 agents without any retraining needed. But how does CWM work? The model starts with the current world state, a single video frame or image, and a list of textual descriptions for each agent's intended action. Each action is treated as its own conditioning signal. Step 1, the text to condition. Each agent's action description is processed using the powerful text encoder. In the paper, they use TX-XXL. This produces a latent representation that can condition a video diffusion model. Step 2, per agent prediction. The video diffusion model is run separately for each agent using the current frame plus that agent's action as the conditioning input. This outputs how that one agent would affect the world. Step 3, all individual predictions are merged using the composable diffusion trick where each agent contributes a score term. This mathematically combines the independent predictions into a unified joint effect. Step 4, sampling the future frame. The diffusion process is run using the composed score. The output is a new predicted frame that reflects all agents' actions simultaneously. The final output is the model produces a coherent next world state that accounts for physical interactions, object manipulation, and visual dynamics of multiple agents, something a single agent models can't do. So the training process starts with stage 1 being a single agent. The model is first trained on data where only one agent acts at a time. The reason for this is that the diffusion model can learn disentangled effects. How one agent picks up an object, how one agent moves, how one agent places something. Training in isolation prevents interference between agents' actions during early learning. Then we move to the compositional joint action training. After learning individual action effects, the model is fine-tuned on episodes where multiple agents act simultaneously. However, it doesn't just learn joint actions directly. Instead, it uses a composed score function that we spoke about earlier, combining each agent's predicted effect into a single multi-agent prediction. The action conditioning. Every agent's action is turned into the text prompt and encoded separately. For example, Alice picks up the green-brown piece, Bob moves right, Charlie waits. Each of these creates its own diffusion conditioning channel. If the model tries to learn multi-agent dynamics from scratch, the signal becomes entangled and noisy. By first mastering single agent behavior, the fine-tuning stages become far more stable. The outcome? This two-stage training pipeline leads to a world model that accurately predicts multi-agent interactions even in complex visual environments. The agent-to-present loss scaling. When multiple agents act in the same scene, their actions affect different parts of the world. For example, if an agent A is picking up an object on the left, the model shouldn't care about the right side when learning the action. Standard diffusion loss treats all pixels equally, so irrelevant regions introduce noise, gradient from one agent interfere with others, and training becomes unstable. But ADLS, for each agent combo, computes a region of influence, roughly the part of the frame where the agent's action could change the visual state. ADLS then increases loss weight inside the agent's region and decreases weight outside the region. This makes the model focus is learning where it matters, which dramatically improves sharpness of predicted frames, localization of action effects, separation of each agent's visual contribution, stability, and joint action fine-tuning. Without ADLS, multi-agent predictions become blurry and inconsistent. Overall, ADLS ensures that the compositional world model learns clean agent-specific effects, which is essential to accurate multi-agent simulation. World reconstruction. Again, the problem here is each agent has only a limited first-person view camera. No agent sees the whole environment, which makes cooperative planning difficult. However, in the steps for world state reconstruction, each agent RGBD data image is turned into a partial 3D point cloud that represents the part of the environment visible to the agent's location. In step 2, the orthographic projection. These partial point clouds are projected into a top-down 2D map. This is important because a top-down representation removes perspective distortion, helps locate objects spatially, and creates a consistent format for planning. In step 2, you have diffusion and painting. The combined map from all agents still has its gaps, areas nobody sees. Combo uses image and painting diffusion model to fill in missing information, generating a plausible and complete world map. In step 4, a single 2D world state map image that approximates the full environment is created. The planner uses this unified map instead of raw camera inputs, making the planning process far more stable and tractable. Also allowing Combo to operate when objects are occluded, agents block each other's view, or important areas are not currently visible. Again, this is important or crucial for multi-agent cooperation. Now we have the action proposer component. It was the action proposer, the intent tracker, and the outcome evaluator. These are those 3 parts I spoke about earlier. The role of the action proposer is to be responsible for suggesting what each agent could do next. Instead of outputting a single action, it produces a set of possible actions that are visually grounded in the reconstructed world state. A vision language model, or VLM, similar to a large multimodal transformer, takes the top-down world state image and a description of the goal. It then generates action candidates such as Alice moves to the blue piece, Bob picks up the green plate, Charlie waits. The reason for the proposals is planning in a complex environment requires exploring many potential features. If the proposer gave only one action, planning would be greedy and prone to failure. But by offering a diverse set of plausible actions, the tree search can explore alternative strategies, avoid dead ends, and consider creative solutions. Each proposal becomes a branch in the Combo's planning tree. The breadth of the tree is directly determined by how many candidate actions the proposer outputs. The impact is a strong action proposer dramatically improves long horizon cooperation, pushing the agents toward useful goal-oriented behaviors. The next module, the intent tracker. This helps each agent understand what its teammate might do. This is essential because in realistic environments, agents cannot see others' hands. They must infer intentions from behavior and visual context. The model works by taking in inputs such as the reconstructed current world state, one or more previous world states, and the overall goal or task description. A VLM processes the sequence and outputs one or more likely next actions for each teammate. Examples would be Bob might pick up the burger bun. Alice is likely to move toward the cutting board. Charlie is waiting for the plate. Without intention prediction, an agent may reach for the same object as someone else, block another agent's movement path, or undo an agent's progress. During the search tree, the intent tracker fills in the missing half of multi-agent actions. The agent proposes his own action, and the intent tracker predicts what teammate will probably do next. Together, they form a joint action that the world model can simulate. The expected outcome is that the intent tracker improves multi-agent coordination from tasks requiring shared objects or precise timing. And here we have the outcome evaluator. The role of the outcome evaluator is once the action proposer generates candidate actions, and the intent tracker predicts what teammates might do, the compositional world model simulates what the future could look like. The outcome evaluator is responsible for judging whether the simulated futures are good or bad. The model works by taking as input predicted next state image generated by the diffusion model. A VLM then analyzes the future frame and outputs a scalar scoring reflecting how close the agents are to completing the task, whether the predicted state makes physical or logical sense, and whether the agents are making progress or wasting steps. Examples of what it evaluates. Is the object closer now to the destination? Did the wrong agent pick something up? Did the predicted frame produce physically impossible configurations? Or is the team moving in the correct direction? Without filtering, the tree search would explore many unrealistic or unhelpful futures. For instance, diffusion models might occasionally teleport objects or mishandle occlusions. The outcome evaluator ensures that planning never exploits visual artifacts. It only accepts possible goal-advancing states. The evaluator acts as a critic, guiding the planner. Good futures get expanded further. Bad or impossible futures get pruned immediately. And so now we have the tree search planning. Planning in multi-agent visual environments requires exploring many possible futures. Tree search allows the system to evaluate multiple action sequences and follow the most promising one at each step. It works by the system reconstructs the environment from partial views. The action proposer generates a diverse set of possible next actions for the main agent. The intent tracker fills in what the other agents are likely to do next, creating a joint action for each branch. The compositional world model uses diffusion-based simulation to predict the next world state for each junction action. The outcome evaluator analyzes each predicted frame and returns a score reflecting goal progress, realism, and coordination quality. Combo keeps only the top scoring trajectories. All others are pruned, making the search efficient. After each agent executes one action, the system reconstructs the world again and repeats the process. Because of the synergy present in structured action proposal, intent predictions, compositional simulation, and outcome scoring, Combo is able to plan several steps ahead while staying responsive to what's actually happening. For the experimental results overview, Combo is evaluated in 3 environments designed to stress test multi-agent cooperation under visual constraints. TDW requires assembling puzzle pieces in 3D environments. TDW Cook involves multi-step cooking tasks where agents must handle tools and ingredients cooperatively. And then the 2D Fetch is symbolic environment where agents must coordinate moving, pressing buttons, and retrieving items. In all the benchmarks, Combo achieves the best success, whereas baselines like MAPPO and recurrent world models completely fail. Combo performs reliably due to the ability to simulate future states compositionally. Combo's completed tasks with fewer average steps, indicating more efficient cooperation. Agents implicitly know how to divide labor, avoid interfering with each other, and perform steps in a goal-directed order. Baseline models frequently produce unstable or noisy predictions, leading to poor planning. Combo's diffusion-based compositional world model generates clean, coherent future frames, which dramatically improves planning ability. Even when tested with fewer agents, again, Combo was trained with 2, 3, and 4 agents. Combo maintains strong performance. This is likely a direct benefit of the compositional design that does not depend on a fixed agent account. I'm sorry. So, key strengths or the takeaways. Compositionality scales to larger teams. Tree search allows long horizon reasoning. Compositional world model produces visually coherent predictions. However, the limitations, Combo requires heavy compute and may not operate in real-time settings or in a fully unstructured real-world environments. The author stated that next or future directions would be with faster generative models and better 3D reconstruction. Approaches like Combo may become practical for robots, multi-agent drones, warehouse systems, and embodied assistants. In conclusion, Combo moves beyond traditional reinforced learning and predictive models by introducing compositional world model tailored for multi-agent cooperation. The combination of visual language model guided planning, future state simulation, and compositional diffusion is a major step forward. Pending your questions, this completes my presentation.